Perfect. So thanks for the introduction. This last presentation will change a bit the topic compared to the previous one. It's a presentation dealing to the effect of hydrogen of the mechanical properties of an advanced high-strength steel, the QMP 1180 or 1180. It's an advanced high-strength steel that is used for application of automotive body-in-white components, so automotive car body component. And in this presentation, we'll see the material microstructure of the as-received material. We can see how we can model the hydrogen diffusion in our material, and so understand what are the properties that can be used for modeling the hydrogen diffusion. We'll see through experimental tests what are the effects of hydrogen intake on the mechanical properties of this material, and also the effect of hydrogen on the fracture mechanism of the broken specimen that we obtained. The steel, as I said before, is a quench partition, advanced high-strength steel grade 1180, so a low carbon steel that has not a very specific chemical composition. More or less the carbon content is 0.3, but what the manufacturer have to guarantee is the ultimate strength of the material, that is the grade of the material. Quench and partition steel belongs to the third generation of advanced high-strength steels used in automotive applications, so very new steels developed for increasing a bit the stamping properties of the material. Quench and partitioning means that the material is obtained by reaching the austenite, so austenization phase, then quench, but the quench is not finished, so the quench is stopped at a temperature that is above the martensite finish temperature, so the quench is stopped at in a condition where there is a significant portion of retained austenite in our material. Then the specimen is a bit held at a temperature that is a bit higher than the temperature of the quench stopping step for the partitioning phase, so for allowing for a diffusion of carbon outside the martensite and migration into the retained austenite phase. So the final microstructure of this material is composed by retained austenite, ferrite island, and a base of martensite that is more or less a tempered martensite. It's a very interesting material because it has very nice stamping properties, so formability properties, but due to this retained austenite content, it's a material that can present risk of trip effects, so transformation of austenite into martensite due to application of strain that can be the strain applied during forming, or the strain that can be applied on our car body due to an accident, due to some that is not the unforeseen events that can change the microstructure of our material and produce fresh martensite. This fresh martensite can be seriously affected by hydrogen, and so this is the reason for this research and the reason that is behind this project, because today I'm disseminating some preliminary result of a PNR project that I'm carrying out in Pisa and together with the colleagues of the University of Bari and Padua. And let's go with the material and methods and the material that we have. As I said, we have quench and partition steel, thickness 1.2 millimeter. In the received condition, it's zinc coated. So it has a coating that can act as a barrier for hydrogen intake, but also a barrier for hydrogen desorption. For our test, we removed the zinc coating for allowing us to introduce hydrogen in the material via electrochemical charging. Electrochemical charging that was carried out due to electrolysis in an aqueous solution of sodium chloride and ammonium thiosanate. In this case, only room temperature testing. From the steel sheet, we extracted samples at different angles with respect to the rolling direction, so 0 up to 90 degrees, so along the rolling direction, and orthogonal to the rolling direction. We carried out slow strain rate tensile test, so tensile test with a slow strain rate that allows for hydrogen diffusion during the mechanical loading. After the test, we measure the hydrogen content via hot extraction method with two kinds of mass spectrometers that we have in our laboratory in Pisa. The sample is just a simple dogwood sample without nothing say special. Say just 6 millimeters width, and the thickness is obviously 1.2 because the samples were directly laser cut from the steel sheet. Just take a brief look to the microstructure. As I said before, the microstructure is caused by tempered martensite, more or less, so a martensitic matrix with some austenitic island that are just the white portion that you can see here in this micrograph. And also, if we go to look into in detail, we see the classic appearance of the tempered martensite, almost isotropic martensite, so without any particular effect due to rolling. In this case, we are observing a sample where the rolling direction is the vertical direction, while the transverse direction of our sheet is the horizontal one. Also, if we go to take a look in the thickness of the sample, so with micrograph where the vertical direction is the thickness of our sheet, while the rolling direction is the horizontal direction here in our pictures, we can see some small traces of rolling. You can see these segregation bands that are here, just here are segregation bands of retained austenite. But apart from this small effect, the material seems to be quite isotropic due to the martensitic microstructure. So what we can do when we have to start dealing with hydrogen, first of all, we have to have an idea of how we can model the hydrogen diffusion in the material. The hydrogen diffusion in the material is governed by the well-known Fick's laws, where we need to understand and measure the apparent diffusivity coefficient, so the coefficient that is multiplied with the gradient of the concentration for having an estimation of the hydrogen flux that is moving towards the material or within the material, and also for introducing it in more complex models that, apart from this just simple diffusion, introduce the effect of hydrogen traps, so material irregularities like grain boundaries, dislocations, and or defects that can act as hydrogen traps, reversible or irreversible, and can govern how the hydrogen diffuses in the material or how the hydrogen accumulates in some region of the material. We measure the effective or apparent diffusivity coefficient through the Van Noten-Stachurski cell. So we have just our sample that is cut from the steel sheet in the middle between a charging and a measurement chamber. The tests were carried out at 20 degrees, so room temperature as the other test. And we tested the material both in the as-received condition, but also in a pre-strain condition. So we took a sheet, we applied a pre-strain up to 5% up to now in the final portion of this project that has still 2 or 3 months of work to be done. We'll test also different strain levels. Up to now, we tested only 5% strain. And what we can see is that if we see how the flux, hydrogen flux that passes toward the sample is as a function of the normalized time, so time normalized by the thickness of the sample, we see a difference due to the strain. Due to the strain, because having strain means, say, introducing additional dislocation. Dislocation works as hydrogen traps and affects significantly how the hydrogen diffuses in the material. So the evaluation of the effect of hydrogen have to be carried out both on the as-received material, but also on strain material, because this material is a material for cold stamping, and where the strain that is applied to the component is fundamental for understanding the effect of hydrogen on our component. Apart from that, we carried out also an estimation of the energy of the traps due to hot desorption method and with the mass spectrometer, the TPD workstation that we had. With this material, we saw only one peak in terms of hydrogen signal when with respect to the sample temperature. It means that it seems from this preliminary investigation that we have only one kind of traps. It seems to be reversible traps. It's a something that we have still to investigate better and to understand exactly the contribution of the retained austenite in this behavior and this estimation of the energy traps. If we pass to see what happens in terms of mechanical properties of the material, first of all, as we can expect from the microstructural examination, the rolling, the direction of the extraction of the sample from with respect to the rolling direction doesn't affect so much the mechanical response of the material. The yield and ultimate strength are more or less unaffected. Only samples extracted orthogonal to the rolling direction presented just a quite lower elongation at fracture. Now, if we have to see what happens in terms of the effect of hydrogen on our mechanical properties, what we can see here, we have different tensile curves obtained through slow strain rate tensile test at different hydrogen content measured on each sample at the end of the test. So we have two curves for the hydrogen-free material, or having an idea of the dispersion of the data, and the other curve are from 0.8 particle per million in weight of hydrogen up to 2.1. It's better. It's also more simple if we look here on the graph on the right side, where we have the ultimate tensile strength of the material and the elongation at fracture reported as a function of hydrogen content, where we can see that up to a content of above 1.5 in terms of hydrogen content, we have no effect on the ultimate strength of the material, while the effect on the elongation at fracture starts to happen at a content that is a bit lower, but until at least 1 particle per million of hydrogen, also the elongation at fracture is not affected. If you consider the result that the preliminary result that we have and the scatter that we measured in the as received material. Also, if we go to investigate what happens from samples extracted in a direction orthogonal to the rolling direction, the behavior is quite similar. Also here you can have the curve of the two hydrogen-free curves and the curves that are related to different hydrogen contents. And here the result presented in the same way as before. Also in this direction we saw that the effect of hydrogen is a bit anticipated. It moved towards lower hydrogen content in direction orthogonal to the rolling direction, as is also typical of other advanced strength steel martensitic materials. Those materials are a bit more sensitive when the properties orthogonal to the rolling direction are investigated. And here you can have the comparison of the two plots, so ultimate tensile strength and the elongation fracture, how they were related to the hydrogen content. And as I said before, in the transverse direction, the material is a bit more sensitive to hydrogen. In terms of ultimate strength, the threshold of 1 ppm is still valid, but in terms of elongation at fracture, the decrease started at lower values. We have an outlier here that is something that we have a bit to investigate better in the final part of our project. If we go to see what happened to the fracture surface of our sample, we can see that without hydrogen intake, we have a surface with significant ductility, how we can expect. When we have a significant hydrogen intake, we pass to an intergranular fracture surface, so a very brittle fracture surface with a huge difference compared to the surface without the hydrogen. So material sensitivity to hydrogen is something significant, and it's worth investigating because this surface is representative of very brittle behavior. If we go to see what happens to material with a lower hydrogen content, here we can see that the material behaves globally as a ductile material with less ductility. So you can see that the imports are less elongated. We have some traces of transgranular fracture. And in the segregation band that we can see due to rolling in the middle of the sample, where retained austenite is more present, we can see that in this region we have brittle failure and intergranular failure with secondary cracks and brittle and the typical traces of a brittle failure here. And also because probably this region worked as a hydrogen trap that created fresh martensite while the specimen was subjected to mechanical loading. Just to conclude, we investigated also the effect of typical material alteration that can be present on the material, so resistance spot welding and cold stamping. Here we are just carrying out some preliminary tests, and so just some brief results. When the material is subjected to resistance spot welding, the material behavior changes a lot compared to the resistive material, and the sensitivity to hydrogen becomes something. The sensitivity becomes increased compared to the standard material. Here you can see that with the content of 0.9 particle per million of hydrogen, we have an abrupt change from a ductile fracture surface to a brittle fracture surface with intergranular fracture also here. And also, if we investigate the effect of a 5% pre-strain level, pre-strain carried out at 20 degrees or 50 Celsius degrees, we have some significant effect of hydrogen intake. In this moment, we investigated only the portion of high hydrogen intake in our samples. Now we have to start investigating the low hydrogen content. Also here you can see that if we pass from the hydrogen-free pre-strained material, so with less elongation due to pre-strain, we have a ductile surface. When we have an hydrogen intake, the fracture surface becomes very brittle with also here intergranular fracture. It's clear that this is a material with 4 particles per million of hydrogen that is a significant intake. And so just to conclude, in this moment, we preliminarily assess the hydrogen sensitivity of our material, so the hydrogen embrittlement sensitivity of this material. This material seems to be prone to hydrogen embrittlement, in particular when hydrogen is present at high contents. And the hydrogen sensitivity is affected by the direction towards the rolling direction, and most importantly, by the presence of alteration in the material microstructure, like the alteration that are typical of components in real applications. So welded region, heat-affected regions, and pre-strained regions. And so, thanks for your attention, and thanks to the project that is this activity was carried out within the framework of the MOS project and the closed call for scalability in big project. That is the project I'm working on. So thank you for the attention.